to all and welcome to this lecture. We are in module 9, lecture number 3, drain-induced barrier lowering. In this lecture, we will discuss about an important short channel effect, that is drain-induced barrier lowering. We will also see the punch through effect which is happening in short channel devices, and we will see how we can incorporate the short channel effects what we have discussed so far in our model which we have derived for long channel MOSFETs. So, these are the learning outcomes of this lecture which helps you to understand the mechanism of drain induced barrier lowering in short channel MOSFET by focusing on drain field penetration into the channel region. We will also discuss about the impact of Dibble on weak inversion operation by examine its effect on off state leakage current and subthreshold slope. We will see the impact of punch through in short channel devices. So, let us do a quick recap. In previous lecture, we were discussing about charge sharing effect. We said that when the channel length or the width of the MOSFET is reduced, then the gate charge is shared from source and drain side, and hence the effort of gate voltage is reduces in some sense, and in some it will increase. So, we have discussed when the channel length is small, ultimately that was the first charge sharing effect. We said that the charge shared by the drain and source ultimately reduces the charge controlled by the gate, and we said that QB dash by QB is smaller than 1, which was giving me that gamma 1 cap is smaller than gamma, and hence the threshold voltage reduces because of charge sharing. That is what we found, that when you plot the threshold voltage with channel length in x axis, when you reduce the channel length there will be a threshold voltage roll off. To improve this or to mitigate this threshold voltage roll off problem, we suggested a possible solution, that is halo implant. Halo implant is nothing but create a halo pocket doping near the source and drain region to increase the concentration of these regions highly in local regions without affecting the body effect coefficient of complete substrate. We have also seen two different processes related to the width scaling. One is STI, that is shallow trench isolation, another is LOCOS, which is local oxidation of silicon. In STI process, we said that because of the width scaling, the fringing lines will be becoming significant, and hence the overall capacitance seen by the gate will increase, which ultimately decreases the threshold voltage, because we found that gamma 2 cap by gamma is equals to COX by COX 2 cap, where 2 stands for the second charge sharing effect what we have discussed. Accordingly, we said that the threshold voltage is reduced in STI process when you plot the threshold voltage graph with respect to width scaling. Then when you reduce the width, ultimately you will get a threshold voltage roll off. So, this is VT2. We have also discussed about LOCOS process and said that in the LOCOS process the gate should give an extra effort to deplete the side wall depletion region. To create this side wall depletion region, ultimately the gate charge shared by the gate is more than the total charge, that is QB, which ultimately increases my gamma 3 cap, and we found that if gamma is increases, the threshold voltage increases. So, in the LOCOS process, when you plot a graph of threshold voltage which is VT3 cap with width scaling, then when you reduce the width, the threshold voltage increases. So, let us see the another short channel effect, which is drain induced barrier lowering. The drain induced barrier lowering is a severe short channel effect in which the drain voltage influences the channel potential near the source. To understand this, let me plot the band diagram of basic MOSFET. For example, consider a MOSFET with channel length very large. So, this is channel length, this is the drain region, this is the source region, and this is the oxide. Considering uniform substrate and the gate voltage which we are applying is exactly equal to flat band voltage. It means there is no extra charge pile up in the surface. We have already discussed what flat band voltage in our previous lectures. For the sake of simplicity and understanding the band diagram, at the very first stage we are considering VDS is equals to 0 or VDB is equals to VSB. Now, if I plot a band diagram of this device along a cut line AA dash, then you will see two PN junctions. One is N plus P here and there is PN plus junction here. So, considering there is no current flow because of these biasing condition, as the gate voltage is just equal to flat band voltage and there is no drain field. So, the Fermi level is aligned, and when you make a band diagram at the N plus side you will get this is conduction band, this is valence band. Similarly, at the drain side you will get the same structure. However, in channel which is P type you will get this is valence band and this is conduction band. If you join this you will get this kind of band structure. Okay. For the sake of simplicity we are only drawing here the conduction band edge. So, this y axis is nothing but energy in electron volts and x axis is along the dimension or along the device, where this side is source, this side is channel and this side is drain. It is clearly visible that at the N plus P junction we do have built in potential which is phi Bi, right. That is what it is visible here, that is phi Bi. So, the electron available into the conduction band of source will not get enough energy to surpass this barrier, and hence we do not have ideally no electrons at the channel coming from the source. Now, consider a case when you increase VGB greater than flat band voltage. It means you are applying a positive field lines. If you apply a positive field line, the surface potential in the channel is increases. If the voltage increases, we have already discussed, the potential energy reduces. It means the barrier is get lowered, and this 2 shows the lowering of the barrier at the source side. So, the electron which was available in the conduction band of the source, now they can easily move or diffuse towards the channel, but still as there is no horizontal field coming from the drain, the current is 0, right. So, the electrons are here. Now, in the third case what we are doing, we are increasing the drain voltage. If you increase the drain voltage here by an amount VDS, as we are plotting in energy axis, you need to multiply by Q. So, Q VDS unit will be in electron volts. So, the band will get lowered because you are applying a positive voltage, the energy will go lowered, and hence this electric field will be transferred in energy to electron, or in other way we can say the electron acquire the energy because of this field, and ultimately it will roll down and reaches to drain. This gives rise to a current IDS. That is what we have already discussed when we were discussing about the basic fundamental current flow in MOSFET. Now, let us do the same analysis in short channel devices. Considering my MOSFET is like this, you have N plus and the length of the channel is very, very small. In that condition you do have a depletion region and some amount of charge is shared by source and drain. That is what we have discussed in previous lecture when we were discussing about charge sharing effect. Because of this shared charge, the surface potential is rises itself, in the sense even if you are not applying gate voltage, because of the charge sharing effect, the some portion of the channel is already depleted, and hence the surface potential is rises up, meaning the surface potential for line 1 for the same gate voltage is equals to flat band voltage is lowered by some amount, and it is not touches this phi bi because of charge sharing effect. Now, what we are doing, we are increasing the gate voltage by the same amount which we used here. So, the barrier is get lowered and showed by a line 2. So, all the carriers will coming here in the channel from the source. Now, you increase VDS. If you increase VDS, this will pull down your conduction band, right, and you just focus on this region which is source channel barrier. Here, pulling down the conduction band by applying proper VDS is not affecting the barrier. However, here when you apply the VDS in short channel devices, this barrier will lower the source channel barrier also. This phenomena is called drain induced barrier lowering. Barrier lowering. And what is the important aspect which is changed in the device is called threshold voltage, because this lowering of the barrier is ultimately related with the threshold voltage. We can simply say in long channel devices the threshold voltage was fully captured by gate voltage, right. The amount of gate voltage you required to cause depletion and inversion. In the inversion, the carrier will come from source side and causes the plenty of electrons available in the channel. That is what we defined as threshold voltage. However, here the threshold voltage is now become a function of VDS. That is actually called drain induced barrier lowering, or in general DIBL. So, we will see how we can calculate the change in the threshold voltage due to drain voltage. To do so, we need to go for two dimensional analysis, as we have already discussed in previous short channel effects like in CLM, like in charge sharing, that when the depletion region expanded near the drain and source, then this region we need to solve two dimensional Poisson equation. One dimensional Poisson equation was good enough for long channel devices. However, when you are going for short channel devices, you need to solve two dimensional equations. So, to move further, we are again considering that we do have a device which is having smaller channel length, and when you increase VD, then near the drain the expansion of the drain region is the expansion of the depletion region is there, and near the drain Qi approaches to its minimal possible value, because Vd achieves its saturation value or maximum value, and hence to maintain a constant current Qi dash and Vd max product will adjust itself such that Qi will go its minimum possible value. So, just in this case, which we have already defined in previous lecture when we were discussing about channel length modulation, let us consider this is the length Lp. In this case, in this region we said that Qi approaches to its minimum possible value, and hence there is no immobile charge carrier in principle, right. So, considering a very ideal case, we can simply rewrite a two dimensional Poisson equation here, which is delta square psi xy, because your potential is now function of x dimension and y dimension, again mentioning that x is this direction and y is this direction throughout our course. So, delta x square plus delta square psi xy divided by delta y square is equals to, for the sake of simplicity, we are converting the two dimensional Poisson equation to two dimension Laplacian equation. The same analysis we have done when we were discussing about CLM. Here the surface potential or the potential psi xy is nothing but can be split into two parts. One is solely a function of x and one is solely a function of y. We can simply define as x and y. To go back and rewrite this equation, we can simply write delta square x into y divided by dx square plus y into d square y divided by dy square. This will become x is equals to 0, or we can simply rewrite as 1 over x delta square x divided by dx square plus 1 over y d square y by dy square is equals to 0. This differential equation can be only solved when these two parameters are equal to constant, meaning 1 over x delta d square x divided by dx square is equals to, let us say, k square, and 1 over y d square y divided by dy square is equals to minus k square. We have already done this kind of analysis when we were doing for CLM or channel length modulation. This will give you two solutions. One is x is equals to psi of x is nothing but a e to the power of x k plus b e to the power of minus k x, and y is equals to psi y is equals to c cos of k y plus d sin of k y. So, I am not repeating the same analysis here. We have considered some boundary condition to calculate this value k by using some eigenfactors of tan function, right, and then we got k is nothing but epsilon O x divided by epsilon s into T O x into dB. When we were discussing about CLM, we said that L A was the characteristic length. Here we are defining a new parameter as lambda, which is nothing but 1 over k, and this is characteristic length. So, lambda is nothing but square root of epsilon s divided by epsilon ox into T ox into dB divided by beta 3, where beta 3 is some fitting parameter. Now, if we can focus on how my potential varies in x direction, we will see that it is directly proportional to e to the power of minus x by lambda, where k is replaced by 1 by lambda, right. Or I can simply write the change in potential along the x, along this side, right, is equal to some delta phi d into e to the power of minus x by or lambda, or x can be replaced by L, where L is the channel length. So, again I am not doing a complete derivation, I am just giving you an intuition how you can proceed for this final solution. Now, here phi d is the change in the potential, right, the change in the potential at the source side, which is nothing but phi bi minus phi naught. The change in the potential at the source side, ideally it should be phi bi, which is the built-in potential at the source side, minus phi naught, which is the surface potential acquired because of the applying gate voltage. But as we are discussing that in short channel effect, the dibble will come into picture, meaning the effect of drain voltage will also come into picture. So, you need to add VDS e to the power of minus L by L, and this 3 is again a parameter which is coming because of fitting of these equation into the well defined equation. Now, we need to use, this is 3, now we need to use a negative sign. Why? Because the threshold voltage is decreasing, because of increase in VDS the threshold voltage is decreasing, and hence we define the change in the threshold voltage due to dibble is minus of 3 into phi bi minus phi naught plus VDS into e to the power minus L by lambda. Again, for sake of simplicity, we can simply solve this equation further, considering that exponential can be converted into power law. So, this exponential of minus L by lambda is can be replaced as L to the power of some constant, which is let us say beta 6, and these factors can be represented in terms of source to body voltage. To give you an idea how my threshold voltage change with source to body voltage, so we can simply rewrite as Vt dibble is equals to minus some constant we are taking beta 4 plus beta 5 into Vsb into Vds, and instead of using exponential law we are using a power law, that is L to the power of minus beta 6. So, you can write as L to the power of beta 6. Strictly speaking, this is the equation which will derive with many approximations, which give you an idea how my dibble relates with the voltages drain voltage and VSB. Now, let us take two parameters to understand how you can relate the dibble with VSB, and other parameter is substrate doping. The first parameter we are taking as substrate doping. So, this is the MOSFET where N plus are source and drain, and this is P type body. So, the substrate doping is nothing but Na. Now, question is what will happen if you increase Na? So, let us see and validate our equations and find out whether dibble will increase or decrease. So, if you increase Na, then what will happen? The expansion of the depletion region will be reduced, right, because if the doping concentration here is increased, the expansion of this depletion region will be reduced, and hence dB will reduce. If dB will reduce, what about lambda? It will reduce. If lambda will reduce, ultimately e to the power of minus L by lambda factor will reduce, and hence dibble will reduce. So, if Na is increases, dibble reduces. We can understand this physically as well. When you increase the doping, right, then you are actually reducing the expansion of the depletion region, meaning you are providing a blockage or hindrance to the feed lines which are coming from the drain. Ultimately, you are blockage to the screening of the feed lines towards the source. That is what, by increasing the substrate doping, you can reduce the dibble. The second question is what will happen if you increase VSB? This is also obvious. When you increase VSB, the increase in VSB will expand the depletion region, meaning you are providing more leverage to the field lines to penetrate throughout the channel and enter into the source channel barrier, which can be validated through this equation as well. When you increase VSB, dB will increase. If dB will increase, lambda will increase. If lambda will increase, e to the power of minus L by lambda will increase, and hence the overall dibble will increase. So, let us move further and see how this dibble or the change in the threshold voltage affects the characteristic. In previous analysis, when we were discussing about the charge sharing, we said that the threshold voltage is getting affected because of charge sharing, but we said that the impact of charge sharing is only to shift the current characteristic in the x axis, which is VGS, meaning if we plot a current characteristic I ds versus VGS, then this is the characteristic we obtained, and we said that this is my threshold voltage, which is Vt plus alpha into VDS divided by 2. If you include the charge sharing effect, this curve will shift either left side or right side based on different processes, as we have discussed narrow width devices and narrow channel devices, right. So, we mentioned that the charge sharing effect is not affecting your characteristic or not deteriorating your characteristic trend. However, when you go for dibble is also affecting your threshold voltage, but whether it is affecting the characteristic behavior or not, that is what we are going to see. First, as we talk about the threshold voltage or the relevance of the threshold voltage definition is starts when the onset of moderate inversion will consider. So, we will see what will happen in the weak inversion or what is the influence of weak inversion predominantly. So, if we write the weak inversion equation, we know that IDS in weak inversion can be given by some constant into e to the power of VGS minus Vt divided by n into phi t into 1 minus e to the power of minus VDS divided by phi t. We have already discussed this equation when we were discussing about the weak inversion and converting the weak inversion modeling from surface potential and charge based to a terminal voltage based, right. Now, what is happening here, because of dibble the threshold voltage is changes, right. So, let us consider my threshold voltage is changed to a smaller value of delta Vt. So, I can rewrite this equation as Im dash e to the power Vgs minus Vt minus Vtm or delta or dibble, right, divided by n into phi t e to the power 1 minus e to the power minus Vds divided by phi t. So, you can simply rewrite this equation as IDS due to Dibble is equals to IDS for long channel into e to the power of minus delta Vt divided by n into phi t, meaning the characteristic of the on current or the characteristic of the current is also changes. It is not just the shift in the x axis. Now, how it is affecting the characteristic in weak inversion? The two sense we can consider as, first, when you increase the Dibble effect or by reducing the channel length you increase the Dibble effect, then what happens is there will be a shift in this x axis because of reduction in threshold voltage. However, the slope of the graph is also reduces because the change in the threshold voltage increases the leakage, and hence what will happen, earlier you were expecting this graph, but now in this Dibble condition you are expecting the graph like this. So, ultimately the subthreshold slope is getting deteriorated when Dibble effect comes into picture. The phenomena of Dibble is much more severe when you talked about the ID-VD characteristic, right. We have seen, we can see that when you plot the ID-VD characteristic and considering Dibble in weak inversion, then there is a finite slope in ID-VD characteristic. We have discussed that part when we were considering channel length modulation, but here even if the channel length modulation does not hold good or if it is not occurring even, the Dibble allows to penetrate the electric field line through the depletion region away to source channel barrier and affects the current, and hence we get a finite slope in the output characteristic. Strictly speaking, in weak inversion this finite slope is much more responsible due to Dibble. Now, we can define in a hand calculation that Dibble is can be defined as Vt sat minus Vt lin divided by Vds max minus Vd min. I will explain you what these quantities are. Take the mod, this will give you Dibble, right. Here, as we know that the threshold voltage of the device is getting affected by Vds. So, what we will do, let us consider you are having a MOSFET and you are operating a MOSFET at 0.7 volts, that is the maximum power supply of your MOSFET. So, we will keep the drain voltage to 0.7 and calculate the threshold voltage, that is what is called Vt sat. Next, you take the Vds value to be lower, let us consider 50 millivolt and calculate Vt, that will give you Vt linear, and you subtract the difference between these threshold voltage. You can simply see that this threshold voltage is because of drain voltage influenced and this threshold voltage without the influence of drain voltage, right. In general we are assuming that this is very, very small, and hence you divide by the change in the drain voltage. So, this will give you a Dibble. In general the unit of Dibble is what? Millivolt per volt, correct. We will see another short channel effect, that is called punch through effect. The punch through effect is a severe short channel effect that occurs when the source and drain depletion region merge. Though we have seen that the merging of the depletion region from the source and drain causes two other short channel effects, we named it as drain induced barrier lowering and charge sharing. However, the punch through is much more severe. In punch through, the gate will lose its complete control. Unlike Dibble, punch through cannot be modeled by a simple Vt shift because punch through will deteriorate or destroy the complete behavior of the characteristic. Now, what is punch through is, for example, you have a MOSFET like this and the channel length is very, very small. There is a possibility that the depletion region touches each other. When the depletion region touches each other, because you are applying a gate voltage to control the channel, but the depletion region is touches to each other, and hence without the gate control the carrier can move between source and drain, and hence you see the off current or the leakage current is increases significantly. If in this log ID versus VGS graph I say this is the point I choose as on current, and for VGS is equals to 0 I define this as off current, then when the punch through occur because of decreasing L, then I on off ratio is become very poor, meaning the device is not turning off. This is on state, this is off state, almost device is on, which is a huge current flowing in between, right. The punch through effect can be broadly classified as surface punch through and bulk punch through. What it means is this is surface punch through. The expansion of the depletion region from the source side and from the drain side, it merges at the surface. However, there is also a possibility that the depletion region will touches to each other or merges to each other at the bulk. Why? Because we have seen that we can use some VT control implants, VT in the sense threshold voltage. We said that if we want to use the control of threshold voltage expansion or threshold voltage increase or decrease because of charge sharing effect, we can use some halo implants. Halo implants means suppose you are using high doping here near the drain, let us say P plus. So, the expansion of the depletion region in this side will be small, however, the doping at the substrate will be lesser. So, the depletion region can be like this at the drain side and the depletion region can be this like at the source side. This is a merging point where the depletion region will merge in the bulk, that is what bulk punch through. Bulk punch through is more dangerous and severe as compared to surface punch through. Now, if we want to compare between Dibble and punch through, we can simply say that Dibble causes a reduction in threshold voltage, however, gates still have a partial control, while in punch through, whereas in punch through gate completely loses its control, and that is what if we plot the current voltage characteristic, you will see some abnormal behaviors of this current characteristic. Why? Because if you remember, the plot of ID versus VDS shows a nice transition from non-saturation to saturation. If you will not consider the velocity saturation, you will get more abrupt transition, right. However, if you see the ID VD characteristic because of punch through, it is just an abnormal behavior where the current is rising and not saturating, correct. Now, what are the possible ways to reduce the punch through? You can reduce the punch through by using some method to reduce the depletion region expansion. The simplest method is you increase the substrate doping, but as we already commented on this point that you cannot increase the substrate doping everywhere because ultimately it will increase the body effect coefficient. The second method to reduce the punch through is introduce punch through control implants or punch through stoppers, in addition to VT control implants which we have discussed as halo implants, or the other way is maintain the adequate channel length for particular defined technology. Now, we will see how we can combine the short channel effects what we have discussed so far in a single model, because we have a single model for long channel device and we want to preserve that model which we have derived by multiple approximation for long channel devices. But can I do something to preserve that model for short channel devices as well? So, let us do a simple development of a model which includes these listed effects, like the effect of channel length on effective threshold, that is what we have already discussed. When you reduce the channel length, the threshold voltage will reduce. The effect of Dibble, we have also discussed, the Dibble is also reducing the threshold voltage. When you scale the width, then also the threshold voltage is getting affected. Yes, in STI process it will reduce, in low cost process it will increase. Velocity saturation effect, we said that the carrier velocity is no longer linearly rises with Ex and it gets saturated after some critical field, and we also derived the current equation for that is nothing but IDS without velocity saturation divided by 1 plus VDS divided by EC into L, right. The another effect we want to include in our model is effective mobility. We said that in general mobility is suffered from multiple scattering events we discussed as phonon scattering, Coulomb scattering and surface roughness. And we said that the effective mobility can be modeled as mu naught divided by 1 plus a theta divided by epsilon s into QB average plus 0.5 QI average, where 0.5 is nothing but eta E. By solving this equation, ultimately we got mu effective was mu naught divided by 1 plus theta into VGS minus VT plus some theta B into VSB. That is what we have already derived when we were talking about long channel device. And the last, we want to include the channel length modulation. We have also discussed this impact that the drain current IDS can be given by IDS dash divided by 1 minus LP by L, right, and you can simply solve as IDS dash into 1 plus LP by L. Now let us see how can we incorporate these model in our previous model derivation, in our previous derived model, and change the model for short channel effects. The first, second and third model changes the effective threshold voltage. So I can rewrite the threshold voltage equation, which is ultimately captured or governed by L, W, VDS and VSB. These are the parameters which influence the threshold voltage in general. So VT VSB we have already known. For long channel devices also it is influenced by VSB, as VT can be given by as V flat band voltage plus phi naught plus gamma times of phi naught plus VSB. The second parameter is change in threshold voltage due to change in length, and the third is change in threshold voltage due to change in width. So overall the threshold voltage can be written as VT cap, which is a function of L, W, VDS and VSB. Now we will include this threshold voltage definition in our current equation, that is what VGS minus VT. So VT can be replaced by VT cap into VDS minus 0.5 into alpha VDS square into mu into Cox dash into W divided by L. Now instead of taking mu in our basic model, we are taking mu naught, which also captures the effect of effective mobility mentioned in point number 5. So we can rewrite as mu naught divided by 1 plus theta into VGS minus VT. Again VT can be replaced as the effective VT, right, here this equation we are using. So 1 plus theta into VGS minus effective VT, which is a function of L, W, VDS and VSB, plus theta times of VSB into, we are also including the effect of carrier velocity saturation, which is nothing but 1 plus VDS divided by L into EC. That is what we have written here. So ultimately we have included 1 effect, 2, 3, 4 and 5. Now we can also include the channel length modulation by just rewriting in terms of 1 minus LP by L. So this equation can be solved for channel length modulation, and we solve this equation by finding delta IDS by delta VDS to find out what is VDS dash. Strictly speaking, as we have said that the transition from non-saturation to saturation is very smooth, and you cannot find out the distinct value of VDS dash. So here we have included all the possible short channel effect. The only one thing you need to take care of is the threshold voltage is not dependent on VDS dash, but it is dependent on VDS. This point we have already discussed when we were discussing about Dibble. What we said is, if VDS is not enough to reach the value of VDS dash, then also because of the channel length small, there is a significant amount of depletion region, and hence drain region penetrate or drain field penetrate away through the channel and reaches the source channel barrier. Thus the Dibble effect is available beyond the pinch off also, correct. That is what the change in the threshold voltage does not depend on whether the VDS value reaches to VDS dash or not. For any value of VDS, the threshold voltage is changing in short channel devices. That is what here you can see the threshold voltage is not a function of VDS dash, but it is function of VDS. The second point you need to take care of is, if I use this equation to solve for delta IDS divided by delta VDS to obtain VDS dash, then it is guaranteed that this equation gives the continuity in finding first derivative of current. However, when you go for a second derivative of this, there is no guarantee that it will be continuous or not, because the transition we have discussed from the non-saturation to saturation is very smooth, and hence instead of using VDS dash, right, VDS dash, you should replace this as a VDS effective. This is also help you to save or to rewrite your modeling approach, meaning suppose you want to write a code to plot a current, then there will be a part which is non-saturation and there will be a part which is saturation. So, you need to write a if statement in your code, meaning you will mention that if VDS is less than VDS dash, then you will follow the equation for non-saturation, and if VDS is greater than equals to greater than of VDS dash, then you should follow the current equation for saturation. So, to avoid this discontinuity, you can simply use VDS effective. So, let me summarize this lecture. In this lecture, we extensively discussed about drain induced barrier lowering, which is a very important short channel effect, needs to be discussed, as the threshold voltage now become a function of VDS. We said that when you plot a conduction band, then there will be a barrier lowering at the source channel junction, which is a function of VDS, because the applied drain field will penetrate away through the channel and ultimately alters this barrier and significantly influence the threshold voltage. We discussed that the dibble is not only change a shift in the IDVG characteristic, but it will destroy or it will affect the IDVG characteristic when we talk about short channel devices. In addition, we have discussed about punch through, which is more severe, because in punch through the gate loses its complete control. There are two types of punch through, one is surface and one is bulk. We claim that bulk punch through is more severe and dangerous than surface punch through, and at last we have seen how we can proceed with our previous models, what we derived for long channel devices, and preserved those models by a slight modification in the parameter which is actually captured by the short channel devices. In this modeling approach, we need to take care of that the impact of individual short channel effect should be negligible or should be small enough such that they cannot interact to each other. Meaning, if you let us say include a dibble, and at the same time if you are including charge sharing, then both the effect will come together. So, it is really hard to find out what is the impact of dibble separately and what is the impact of charge sharing separately on threshold voltage. That is what, while doing this modeling, we need to take care that these individual effect interaction is very small or negligible. So, we will stop here for today. Until then, take care.